Hello, my name is S.Jaques, and I'm going to talk about solving elliptic curve discrete log using Shor's algorithm. So we're all here, and PQCrypto as a conference exists because of Shor's algorithm. So we'd really like to know, when will it break all of the crypto that we expect it to break? And so to do that, we need to look at Shor's algorithm. Here's a diagram from Wikipedia, and ask, what is the cost to run this? How big does the quantum computer need to be? How good do the qubits need to be? And when we look at this algorithm, we've got these quantum part at the beginning, this superposition, a quantum part at the end for the Fourier transform, and in between we have these sort of semi-classical gates. But in terms of cost, it really looks more like this. The vast majority of the cost is in this semi-classical part. And so this is the part that we want to estimate. And previous work has done some estimates on this. So for elliptic curves, Proust and Zelka sort of started this. They had a lot of ideas, although it was a lot of sort of pen and paper, looking at asymptotic numbers. And then follow-up work had automated estimates, which I'll refer to as RNSL. It was the main source for this work. And there was work last year on factoring, and it was a sort of full stack analysis, including error correction, all the way up to an improved algorithm. We just stick to a logical level, which I'll explain in a moment. But the big thing about previous estimates seems to be that most of the work focuses on minimizing the number of qubits, which makes sense in a way, because right now, here's sort of the best quantum computer, arguably, and it has 54 qubits. So we just can't run Shor's algorithm on it, no matter how much we try, because it doesn't have enough qubits. But suppose that somehow we had the same chip and the same qubits, but we have 5,000 of them. Well, we still couldn't run Shor's algorithm because the qubits aren't good enough. They need to be about 1 billion times better. And so what we sort of expect to happen is not that qubits get 1 billion times better, but they get enough better that we can start to put them together into error-correcting codes, shown here like the surface code. So we'll have the physical qubits, which are like the qubits of today. These are a noisy physical device, maybe a little superconducting chip, and we connect them all together, and so that they work together to produce one logical qubit. So this involves many physical qubits. It's really an abstraction, and it has very low noise because we have all these qubits. So when we're considering algorithms for quantum computers, the number of physical qubits that we need to produce one logical qubit depends on how long the algorithm needs to run and how many gates it needs to run, because that tells us how much noise will accumulate. So if the algorithm takes longer, then we need more physical qubits for every logical qubit. So it's quite possible that a shorter algorithm, but with more logical qubits, will actually require fewer physical qubits. And so ultimately what we're thinking is, maybe minimizing qubits at all costs is not the right approach. So what we did in this work is we considered different trade-offs. So we considered the same as before with the fewest logical qubits possible, and then we also considered the fewest T-gates possible, and then the lowest depth, so i.e. the lowest circuit depth, so the fastest. We have more trade-offs overall, and our most impressive result was reducing the circuit depth by 6,000 times with only 22% more logical qubits. So I think this is probably better to run on physical devices, but this would depend on a deeper analysis. We only looked at the logical level. So the other thing we have is we have Q-sharp code for all of the circuits. And so Q-sharp lets us test them even at cryptographic sizes. And the reason we're able to do this is because we're only considering this classical middle part of Shor's algorithm. So we can simply consider the qubits as being zeros and ones because they never need to be in superposition. And once we have all this, we can test our circuits and then run automated resource estimates. And Q-sharp is pretty good at being smart about these resource estimates. But it turns out that there's actually a bug that was discovered after we ran these estimates that I'd like to explain here. So Q-sharp is nice to work with because all of the qubit management, the gate scheduling, is abstracted away. So you don't need to say, remember exactly where this qubit is. Here's an example of some Q-sharp code. This using statement will allocate 4 qubits, and then we do some operation on all 4 qubits. And we write the code as normal classical computer code. It's sequential. And so naively, you would generate a circuit like this, where this sum op, whatever it does, is run on the 4 qubits sequentially. But Q-sharp will look at this and say, well, there's no reason not to do this, to run these all at the same time. Suppose that this is what SUMOP does. So I've defined it here. It allocates its own qubit, called OX-qubit. It does something on it, and then it releases it. So by release it, I mean it returns it to some state, to the 0 state where we know exactly what it is and we can use it for something else. So again, naively, the circuit would look like what's on the right here, where it allocates a qubit and then releases it. So this has depth of 4, and what Q-sharp will notice is that, well, once the first run of SUMOP releases its qubit, we can reuse that qubit for the second run, and again we can reuse it for the third. So we only need 1 extra qubit for all 4 calls to this extra operation. Of course, you could also parameterize it differently. You could run them all at the same time, and again do it in 1 depth, but we would need 4 extra qubits. Now where Q-sharp has a bug is that it optimizes these separately and doesn't notice that these conflict with each other. If we want to do this in depth 1, we need 4 extra qubits, but it will answer that you can do it in depth 1 with 1 extra qubit. We don't know how much this bug has affected our results. It might not be that much because they seem fairly close to what one would theoretically expect from analyzing the circuits, and there were not significant gains in parallelization when we assembled the circuits together into a larger elliptic curve circuit. And the gate counts are correct either way, and certainly the depths can be achieved, though perhaps with more qubits and vice versa. To go over what the improvements are, to do point multiplication on an elliptic curve, which is what Shor's algorithm requires, has this whole stack of operations we need to do. So we build the multiplication out of several point additions, each of which is made out of modular multiplication and inversion, and those are in turn built out of addition, which is modular addition, which is in turn built out of regular addition. We have some small improvements all up this stack of operations. So at the very bottom, the fundamental unit for a classical algorithm within a quantum computer is the Toffoli gate. So it takes 2 input bits, x and y, and XORs the AND of those bits with a third bit. Now often what we find is that in the circuits we want to build, the third qubit set is actually, it starts in the 0 state. And so we only need to produce x and y in the last register. So maybe there's a simpler way to do this, and it turns out that there is. So this was published a while ago, and so we only need 4 T-gates in T-depth 1 to do an AND gate, and this is in comparison to 7 T-gates for a Toffoli gate. And the adjoint is actually much, much cheaper. We can do it without any T-gates at all, and just with a measurement. And this is again a place where measurements seem to have been avoided in previous resource estimates because for physical systems, they're often quite difficult and noisy. But at a logical system, they probably aren't, or they might not be. At least on a surface code, you need to do so many physical measurements per surface code cycle anyway, that a logical measurement is free. And so this is our overall results for addition. These aren't our circuits, we simply implemented them. If you're familiar with addition circuits, classically you might think it should be a logarithmic depth, and we can do that on a quantum computer, but you can see that we pay a pretty high price in T-gates and qubits. And these sort of optimize for the 3 different strategies we were looking at. So then we can build addition together into multiplication. So this is the multiplication circuit from the RNSL paper. This is a good multiplication circuit, but one thing you'll notice when you look at this is it's a lot of controlled addition. This is sort of school book method. You use the bits of one integer to control addition of multiples of the other integer. Now any circuit you can make into a controlled circuit by going through each gate and making a controlled version of the same gate. So when x becomes a C0, z becomes this conjugated C0. A C0 itself becomes a Toffoli gate, which is much more expensive, and a Toffoli gate becomes, in this case, 3 Toffoli gates and an extra qubit. So adding control to a quantum circuit can raise the cost by quite a bit. So we would actually like to save as much of the cost here as we can. And this is something that is missing from the papers on that design these addition circuits. They just give the addition circuit, but don't really do anything to give a controlled version. This isn't a particularly tricky problem, but we looked through and did the best we could. So here's this logarithmic depth circuit. We found that actually only the gates highlighted in red need to be controlled. So this saves us a bit of cost. And so moving up, there's this other problem with these multiplication circuits, which is that they actually end up producing junk qubits. And so when you, I'm using the square here to make it a bit simpler, multiplication is exactly the same. So you can produce x and x squared, but you end up with these garbage qubits. And they're entangled with your input, so you can't get rid of them, but they also are completely useless. And the usual method to get rid of this is you use a C0 to copy out the thing you want, the x squared, and then you just invert your square circuit, which has the same cost as going forward, and you're left with zeros, and you can reuse those qubits, and you have the output you want. And so RNSL, in their previous paper, did exactly this method, and treated this as sort of this black box. Now this is this function square that you can call anytime you want, and you get the square of the input. The problem is, putting this into a larger circuit, we can optimize a bit better. So this is the circuit that they had. And so this is Weierstrass, elliptic curve, point addition. At one point you need to take the slope between 2 points, square it, and then subtract it from another register. Once you do that, you don't need the square anymore, so they actually uncompute it, and you can see that happening in this circuit. It's a square, subtract, and uncompute. But remember that the square involves this copying out and uncomputing trick. So if we break open what's actually happening, it looks like this. And looking at this, you can see right away, well, actually, these just cancel out, this inverse and this forward version. And the other thing you might notice is that subtraction is much, much cheaper and much, much faster than a square. So really there's no reason to use a C0 to copy it out. We could simply subtract directly. And so we can save this extra register. So the circuit as a whole looks like this. What have we done? We've halved the depth in the gates, and we've used one less ancilla register. So this accounted for a lot of the savings. And we found a way to do a similar thing with modular division. So to compute the slope in the first place, we need to invert what's in the x register, multiply with the y register, and then uncompute the inverse because we don't need it anymore. Again, we can break it open into the circuits themselves and this reduction, and we can see that maybe we could do the same thing and keep the junk qubits from the inversion while we do the multiplication. The problem is the multiplication is a long process, and there's so many extra junk registers that we would need to allocate 2 more just for this multiplication. But what we found was that there are 3 registers, which are junk qubits, but we actually know exactly what they will be. One of them is the modulus p, one of them is 0, and the other is 1. So we can cancel these out, because we classically know what they are, and we can fit everything together. So we can fit the multiplication within these extra junk qubits that we can remove. And this gives a simpler, sort of smaller, and faster division. So this is the full circuit for point addition. One thing I'll point out now is that what the circuit does right now is it adds a classical point to a quantum register. So we have a point in a quantum register, or perhaps a superposition of elliptic curve points, and we want to add a specific point that we know classically to it. So the circuit is entirely made for that classical point. But if you look carefully at it, there's only a few points where we actually use the second point, and it would be really easy to swap them out for a quantum point, so that we could add 2 quantum elliptic curve points. They will be almost exactly the same, because the difference in cost between adding a classical integer to a quantum integer and adding 2 quantum integers is very small. We now have a way to add elliptic curve points, and what Choi's algorithm needs to do is it needs to add a superposition of different scalar multiples of that point. So really we need a point multiplication. We need to multiply points by scalars. And so the usual way you would do this, as just an example, is we have this big number, we decompose it into binary, and we have a circuit that adds up different powers of 2 times p. And by controlling each of these circuits by the input, we are able to add the point into superposition. But classically there's a method to do this, where we window this. And so you can see I've decomposed this binary into 4-bit words, which really look like this, 10 and 176. So we could actually control addition of these multiples of p. Now, so far this is much, much worse, because rather than 1 addition for each power of 2, we have 2 to the k additions for each word. And so this is much, much worse. But what we can do instead is that we can swap the addition for a quantum to add 2 quantum points together, i.e. rather than a point that we know classically to a quantum register, we add together two quantum registers. And instead of adding each point from 0 to 2 to the k times p, we just XOR it into a register. And so just XORing the point in is actually, this sort of builds this superposition of different points, and this is much cheaper than adding them all. And so we have to pay a cost of an extra 2 to the k XORs, but we save k additions. Now because addition is so expensive, this actually works out quite well. We balance this at approximately having k as the log of the cost of point addition. The other thing to notice is that pre-computing all these points is done classically, but we assume this is free. Any adversary we imagine who has this big quantum computer surely has enough computation to compute, say, 2 to the 20 elliptic curve point additions. This is a diagram of our final windowed approach. So we also used signed windowing, which is another well-known classical technique, and we found that if we looked up the points and did the full point addition, it would add extra registers, and we felt like it was more efficient to do it 3 times within the one elliptic curve point addition. So here are our overall results. So what's in this plot is, on the x-axis, the number of logical qubits, and on the y-axis is the depth in t-gates on a log plot. So you can see our work has this sort of curve. You can almost imagine this nice trade-off where as we use more qubits, we can get the depth lower. Our NSL is sort of beyond our trade-off. We can manage to have it faster and smaller. This second graph is also logical qubits on the x-axis, but now it's t-gates on the y-axis. And again, you can see we've improved generally, and we still have some trade-offs, although it's a little less clear because the highest number of logical qubits has a bit more t-gates because it's optimizing for depth. And here are our overall results. If you want to pause the video and examine this table more closely, feel free. The only thing I'll highlight here is that our depth is sort of the most impressive result. We shave about 12 to 13 bits off in most cases. The other thing is that Shor's algorithm generally is very expensive. Even in the best case, we're looking at several billion gates that we need to apply. So this is kind of the first cryptographically relevant algorithm, but it's still going to be a big task to solve it. And what I want to finish off with is talking about things that we tried that didn't work, or things that might work in the future, because I think there's some interesting things going on here. There are different windowing methods for classical computers that don't work for quantum computers, and the main reason is a different cost landscape. For classical computers, pre-computation is expensive. It's as expensive as normal computation, but a lookup is cheap. For quantum computers, pre-computation is cheap because we imagine it's on a classical coprocessor, but lookups are expensive because we need to pay a cost for every point in the table to load it into the superposition. So for these reasons, other classical windowing strategies like combs were ineffective. The other thing was projective coordinates. And so any reasonable classical crypto library is going to be using projective coordinates because they're so much faster. But for a quantum computer, we couldn't find any way to make them work. And the main problem is that they're out of place. And so I want to explain what this means because it turns out to be a big issue for designing these sorts of quantum algorithms. So imagine x and y are integers. We want to do arithmetic. Imagine it's all modular arithmetic. So we can do this addition in place. So the register y is replaced with the output x plus y. We could also do an out-of-place operation, such as multiplication. We have x and y, and we keep both the inputs, but we allocate a new register, and that's where we write our output. Both of these circuits are what we used. What we'd really love is this last circuit, an in-place multiplication. And again, there's no reason this shouldn't be possible, because it is reversible. The thing is, we're building this out of Clifford and T-gates, and so every single gate we build it out of is easily reversible. So any circuit we design has a readily available inverse for the same cost. And looking at what this means is if we invert these circuits, the first one becomes subtraction. It makes complete sense that subtraction would be the same cost as addition. No surprises there. The second is unmultiplication, which doesn't really have a classical analog. It makes sense again that this is the same cost. But the last one, the inverse, is division. So what this is saying here is that in-place multiplication cannot be done for a lower cost than division. And so if you think division is going to be fundamentally more expensive than multiplication, then we can't do in-place multiplication will also be more expensive than out-of-place multiplication. The problem is, if we have only out-of-place operations, then we run into these Pebbling gains. So suppose we're trying to exponentiate by squaring and multiplying. So here we square and we square again and we multiply. But now we have these two extra registers with x squared and x to the 4 that are just sort of junk again. We don't really need them for the full exponentiation. And so we'd like to reuse those qubits. And so to do that, we would have to uncompute the square. But now if we want to uncompute x to the 4th, we need to recompute x squared, to use it to uncompute x to the 4th. And then if we want to uncompute x to the 8th, we would need to recompute x to the 4th again. And so this is a whole problem. It's well known from the beginning of reversible computation. There's general strategies that are available to us, but they add a lot of overhead. And so projective coordinate arithmetic is naturally out of place. What I mean is that if we take the classical formulas and adopt them to quantum circuits, then there's no clear or obvious way how to make them in place. And so we have to play these pebble games to make it work, and the overhead from these pebbling exceeds the savings we can find. With the affine Weierstrass, which we used, which seems like sort of the naive textbook approach, we can do it in place, which makes it better overall. A promising approach here is this idea of spooky pebbling. So this is something from a blog post by Craig Gidney, where he says, well, if you take the extra register and you measure it in the plus-minus basis, then you can free up the qubits in a way that doesn't destroy your superposition. You end up adding an unwanted phase to certain states in your superposition. So eventually you need to uncompute that phase, but in the meantime you have qubits available for you to use. I think it might be possible to improve on our results with projective coordinates and this spooky pebbling. The other thing is that all of our classical circuits were entirely just reversible classical computation, which will be simply less powerful than normal irreversible classical computation. So there's a lot of extra cost for these circuits, which seems sort of weird because we expect quantum computers to be generally more powerful than classical. But the thing is, we couldn't find any ways to use any of the quantum power for the basic operations like addition or multiplication. There were some tricks for RSA that actually use the quantum power of the quantum computer for the basic arithmetic operations. So one of these was coset representation, another was these oblivious carrier runways, and these work quite well, but they work quite well for adding classical integers to quantum integers, and for quantum integers that we never have to double. With elliptic curve arithmetic, we actually do so much arithmetic with two quantum integers, such as multiplying them, that it just is more complicated. We need to double the quantum integers, and this is not well accommodated by these other techniques, and so the noise grows too fast and we can't use them. It could be that there are similar techniques that work well for elliptic curves, but we haven't found them, and I think it's an interesting question to look at. Are there ways to use the quantum power of quantum computers to do basic arithmetic? This is a summary of our results. Thank you for watching.